Next up is tension. This is a pull that is provided by like a rope, a cord, a string, or cable. So pull by rope, cord, I don't care. Now it's a restoring, it's a resistive force. It only applies as much as necessary. And the direction of the force is always along the rope or the cord. Can't draw straight. Okay, so let's say we have this rope suspending some sort of mass. We need to make a few underlying assumptions. Now we know that the rope is going to pull up on the mass, and let's say it's attached to the ceiling, so it would pull up on the mass, and the direction always has to be along the rope. So for the roof or the ceiling, it would pull down. So either way, the direction needs to be along the rope. And the assumptions that we have to be careful of are whether or not this rope has mass, or if its mass is kind of negligible compared to what it's holding or what's pulling on it. Let's say it does have mass, and I'm going to divide it into kind of like 3 chunks. So we'll say top, middle, and bottom. This bottom portion has to support the weight of the hanging mass. Now, if you recall, I said that the gravitational acceleration, so if this mass was in free fall, the gravitational acceleration would be the gravitational force on the object over the mass, so the amount of force the Earth is using on it per unit of mass. Well, we can get the gravitational force on it by some quick algebra. So this bottom portion has to be pulling up with the weight of the object, because gravity, again, it's going to be pulling down from the center of mass with the weight of the object. So in order to hold it there, the bottom portion has to be pulling this much. Now the middle portion has to be pulling on all of this, so it's going to be pulling with the weight of the hanging mass plus the weight of the bottom segment. The top portion would then have to pull on all of that. So it'll pull with the weight of the hanging mass, the weight of the bottom section, and the weight of the middle section. So the majority of the tension is going to be in the top. But if we assume that the mass of the string is negligible, so they're like thin little, practically massless string, same hanging mass, this term here becomes negligible. This term and this term are negligible too. So the tension would actually be felt throughout the entire string. We can treat it as one big section of rope. So the tension along the whole thing would just be the weight of the object that it's suspending. Now I mentioned that tension is a resistive force like normal force. And what I mean by that is the rope is only going to supply as much as it needs to. So if this rope can handle 50 newtons and the weight of the mass is only 20, the rope is only going to provide 20 newtons. Kind of picture this. If gravity is pulling on, or if the Earth is pulling down on the mass with 20 newtons and the rope pulled up with 50, The rope is winning the tug of war here, and this mass would suddenly rise up to the ceiling. That shouldn't happen. So the rope's only going to provide the 20. Now, if we were in an elevator and the rope was suspending the mass and the elevator was accelerating, then that rope would need to accelerate the mass. So it would have to push harder in that instance. So we have to be kind of careful. But either way, let's think of a scenario where we have a 50 Newton rope, but the mass has a weight of, or the pull of gravity is, let's say, 52 Newtons. That rope's not going to last. The weakest part's going to snap, or it's going to come loose from the ceiling, or loose from the hanging mast. Something's got to break here, because that rope cannot handle it. The same thing with a normal force. If you are sitting on a table, and I don't know, maybe it's meant for little kids and you're a big kid. Well, if it can't support your weight, your 52 newtons for a 50 Newton table, you are going to fall through it. So that's what we mean by resistive force. It's only going to provide as much as it needs to. So if you only weighed 20 newtons, the table would only push back on you with 20 newtons, assuming everybody was stationary. So that's tension and a little bit of normal force for you.